Hey everyone. So in the last video we introduced four new identities, the angle sum and the angle difference identities for sine and cosine. And we got used to using these identities, and we practiced answering a handful of different kinds of problems with these identities. But one thing we didn't do was we didn't justify or argue why these identities are true. So that's something I like to do in this video. I like to argue why the last identity, this cosine angle difference identity, is true, is valid. I like to give a proof for this identity. And so we don't have time to prove all of these different identities, but in the activity I've outlined how you can prove the other three identities, starting with this one here that we will prove in our video. So one thing I should say before we begin the proof of this identity is that I don't think this proof is all that enlightening. I don't think that at the end of this proof you'll feel all that much more confident with this identity. And so in that sense, I'm not going to test you on the proof of this identity. I'm not going to ask you to recreate any components of the proof of this identity. The reason I'm giving you this proof is, well, there's actually two. One, I think it's really beneficial to be able to follow a series of logical steps and a really challenging series of steps as well. I think it'll prepare you for having to do this later in other math classes where it will be beneficial to be able to follow a challenging proof. Another reason I'm giving you this proof is because in your homework assignments, I ask you to really explain your work and be able to really build up and justify all of your steps. And so here, I haven't proved any of these identities. I haven't said where they've come from, and it would feel inconsistent to not justify at least one of these when I'm asking you to justify all of your work as well. So let's prove this identity. So to prove this identity, we want to show that the left side of this equation will always give us the same value as the right side of this equation, regardless of the values of u and v. And so one way we can do this is we can show that these two quantities really measure the same thing. The left side of this equation measures the same quantity as the right side of this equation. And to go about showing this, one thing we can do is we can try and make sense of a picture involving the values of u, v, u minus v, and sine and cosine of these angles. So let's draw out these angles and see where these values can appear. So here I'm just going to draw an angle for v. It's not meant to be any special angle, right? U and v can be any value. And so here, this is just some random position for the angle v. It's not meant to be any special angle. And then here, again, let me also draw some sort of random angle for u. Again, it's not meant to be any sort of special recognizable angle. Now, the points on this unit circle, well, their coordinates are given by cosine and sine, right? So cosine of v is going to be the x-coordinate of this point on the unit circle at an angle of v. And sine of v is the y-coordinate at an angle of v. And then similarly at an angle of u, the point on our unit circle is given by cosine of u, comma, sine of u, right? Sine and cosine, they give us the y-coordinates and the x-coordinates on the unit circle at that angle, respectively. And so one thing I can do here is I can connect these 2 points with a line and imagine working with a triangle here. And one thing that will be beneficial for us, actually, and it's hard to see why it would be beneficial for us now, but here, if I take that triangle and I rotate it back by an angle of v, I rotate it clockwise by an angle of v, well, we're still going to have the same triangle. All of the lengths will be the same still, but the positions of these points will be a little bit different. And so here, if I rotate this entire triangle back by an angle of v, well, that angle v will go to an angle of 0. Maybe I'll draw with a different color here. So that rightmost angle, that rightmost side of our triangle will move back to the horizontal axis. Here, our leftmost angle, well, if it's going to move back by an angle of v, and it was already at an angle of u, well, it's going to be at an angle of u minus v. Right, so this is going to be an angle of u minus v. Right, it previously was at an angle of u. I'm rotating everything clockwise by an angle of v. So it's going to have a new angle of u minus v in this new repositioned triangle. And then here, these points, well, this length between these points should be the same because it's the same triangle, just kind of rotated around. And now what are these points in this new repositioned triangle? Well, here, this is the point 1, 0, right? I rotated everything back so that it's one of the side lengths are at the horizontal axis. And then here, this point, well, this is going to be, by the same idea of how we determined the points in the previous example, well, it's going to be cosine of the angle, so cosine of u minus v, comma, sine of u minus v. So that's the position of our point on the unit circle at an angle of u minus v, with from this same triangle just rotated back an angle of v. And so the main idea here is that this dotted line in both of these triangles, the purple one and the orange one, these are the same lengths. And so if we compute the distance formula, or we use the distance formula to compute these lengths, we should get the same value every time. And so this is going to be the basis for proving our identity, so that these dashed lines have the same length. And so let's go ahead and compute these distances using the distance formula. Maybe I'll just write a reminder that the distance between 2 points, so the distance between 2 points between x2, comma y2 and x1, comma y1, well, is equal to the square root of x2 minus x1, the difference in their x value squared, plus the difference in their y value squared, summed together. And so let's go ahead and compute the distances of each of these dashed line segments. First, let's start with this purple one. So here, their points are just cosine of v, sine of v, cosine of u, sine of u. So let's go ahead and find the distance of that dashed purple line. So this is going to equal the square root. It's going to be really big, but that'll be okay. So this is going to be the square root of the difference in the x coordinates. So here that's, what is that? That's cosine of u minus cosine of v squared, and then plus the square of the difference of their y coordinates. So that's sine of u minus sine of v squared. And let's simplify this a little bit. Let's square these expressions out. So whenever we square something like this binomial here, well, we're going to get the square of the first term, so cosine squared of u. We're also going to get the square of the second term, so plus cosine squared of v. And we're going to get 2 times the product of the two, so 2 times cosine of u. I guess I should give myself a little bit more space. I should get 2 times cosine of u times cosine of v. And if that doesn't feel super clear to you, I definitely encourage you to pause this video and multiply that out. But this is what we get. And this same thing happens for the square of the difference sine of u minus sine of v. We'll get plus sine squared of u minus 2 times sine of u sine of v plus sine squared of v. And this will all be under the square root. And so what can we do with this expression here? Well, one thing I'd like you to notice is that this cosine squared of u plus sine squared of u here, this simplifies down to 1. Right, that's the same as 1 by the Pythagorean identity. And similarly here, right, this plus cosine squared of v, sine squared of v, well, this also is equivalent to 1 by the Pythagorean identity. And so if I rewrite this expression now, replacing those parts of our expression with 1, well, we've got 1 plus 1 here, so that's 2, minus 2 times cosine of u, cosine of v, minus 2 times sine of u times sine of v. So this is all underneath the square root. And this is the distance of that dashed purple line. Now let's find the distance of the dashed orange line. So let's go back up. So the 2 points that we're working with here for this dashed orange line that we want to compute the distance between was cosine of u minus v, comma sine of u minus v, and the point 1 comma 0. So the point on our unit circle along our horizontal axis on the right. So this orange distance well, it's given by the square root, and here this is going to be another large square root of the difference in the x value. So here that's cosine of u minus v. Take away, well, the x value of the point on the horizontal axis, that was 1. So we're going to square this distance, or this difference. We're going to add that with the difference squared of their y value. So sine of u minus v. Take away, well, the y value of that point on that horizontal axis, that was 0 squared. And so here, squaring our first expression, first part of our expression, gives us cosine squared of u minus v. Take away 2 times cosine of u minus v plus 1, right? So square of the first term, square of the second term, and then twice the product of our 2 terms. And then for the second square, well, here, minus 0 doesn't really contribute anything. We're really just squaring sine of u minus v. And again, this is all underneath our square root. And so just like our previous example, we have a Pythagorean identity that we can apply. Right, so sine squared of u minus v times cosine squared of u minus v, well, that's going to equal 1. And so I can rewrite this square root as the square root of, well, we'll have 1 from our Pythagorean identity. We have another 1 right here. So this is going to be 2 minus 2 cosine of u minus v. So this is the distance of our dashed orange line. And we were saying that the distance of this dashed orange line should be equivalent, it should be the same as the distance of our dashed purple line. They came from the same triangle, just rotated. And so what's underneath the square root should also be the same, should always give us the same value. So we can set these two quantities equal to one another and try and simplify that equation or that expression. And so here we've got 2 minus 2 cosine of u cosine of v minus 2 sine of u sine of v. So here I'm going to write that in purple. That's 2 minus 2 cosine of u cosine of v minus 2 sine of u sine of v. And we said that this is equal to the distance of our orange dashed line, and we said that that's 2 minus 2 cosine of u minus v. Well, one thing I can do here is I can subtract away 2 from both sides of this equation, and we'll have an equivalent equation. So I'm going to subtract away 2 from both sides of the equation. Another thing I can do is I can multiply by negative 1 throughout the entire equation, right? Multiplying the left side by negative 1 changes these to positive, and this to positive. And then the last thing I can do is I could divide both sides by 2. Right, so maybe I'll just write that below, dividing both sides by 2. And so on the right side, we end up with just cosine of u minus v. And on the right side, well, when we divide a sum or a difference, really we're dividing each term in that sum or difference. So we're going to divide that first term by 2, so we're going to have cosine of u, cosine of v, and we're going to divide that second term, and we get plus sine of u times sine of v. And so this is our result. This is our identity here, right? We have cosine of u minus v is equal to cosine of u cosine of v plus sine of u times sine of v. We've completed the proof of our identity.